Good afternoon, good evening, and good morning to all of our participants. So my name is Stephen Oliver. I'll be taking you through the 270-volt airframe high voltage distribution system and specifications today. And the plane that you see on the title screen there, that's an F-16 Falcon, and that specific plane is the test bed on which a lot of 270-volt DC systems were run. So that actually flew more than 600 flights between 1978 and 2001 before it retired. So when we look at 270 volts DC, we first of all have to ask the question, well, where does electrical power come from on an airplane? And the answer is it comes from the engine and is then generated. So whether it's a turboprop or a jet engine, we have a mechanical rotational force that goes into a generator, and an AC waveform is created. Now, originally in the past, that was a mechanical linkage, and there was a mechanical system which maintained a 400 hertz output, which is why the original aircraft specs, going back to the MIL standards, was 400 hertz. However, that mechanical linkage meant that there was quite a drag on the engine itself, and so it was very inefficient to generate electricity in this way. Now, if you go to an electrical link to create that power, or not a mechanical link, then you can have a much more efficient generator with less drag on the engine. However, as engines speed up and slow down during takeoff, landing, or combat maneuvers, then the frequency will also vary. And it's very difficult to match frequencies if you want to combine sources of power. So what happens is that from every one of these variable frequency generators, which started off life in the late 90s in the UK, you will take this wild frequency, anywhere from 360 to 800 hertz, and then rectify it down to a DC level. And because we're talking about 115 or 200 volts AC, that rectification goes to a natural 270 volts. So 270 volts is a mathematical result of rectifying the 115 and the 200 volts AC, and going DC means that you can, number one, transmit power very effectively, and the second thing is you can combine sources and obviously run a lot of loads from that single bus. So once that's rectified, you get 270 volts DC, and a few things on why 270 volts is the way forward. The first thing is that we minimize the number of power converters in a given network. Obviously, if you transform less, you regulate less, you're not losing the power at each of those stages. It also means that from 270 you can have very high power loads, you can have low power loads. It is a very flexible bus voltage. Again, you can parallel the generators of that power and also parallel the loads, and you'll find that in most airframes the 270 volt DC is in a ring network, which means that if the ring is broken on part of its cycle, then the other part of the ring will maintain the power flow, so it acts as a redundant system. The other thing about 270 volts is that we can do some high voltage stacked batteries, and also now we're getting into the supercapacitor technology for advanced systems where we can store energy in some very, very small and lightweight systems. And supercapacitors are improving by the year and a very good energy source. And also 270 volts DC as opposed to, say, 28 volts, which is used for lower power loads and in some smaller aircraft, is that it comes down to the I squared R loss. So if you've got a higher voltage, it means the current is lower. So our current squared is much reduced, and you don't have to spend as much on copper as you would if you were at low voltage. especially when it comes to larger aircraft. The picture at the bottom is the upcoming Boeing 787-10, nearly 70 meters long, which means that's a long way for us to bus power. So if you're doing it at a low voltage, it would be very inefficient. The bus itself would be very heavy and hot. So going 270 volts DC solves all of these problems. Now, a nod to the military side of the house in really making 270 volt DC a true reality in modern airplanes. Back in 1992, the U.S. Wright Laboratory at Wright-Patterson Air Force Base put out a paper calling for the more electric aircraft. So this is putting more of the loads, more of the flight controls onto an electrical system rather than hydraulics. There are a few technology demonstrators in there that all went into that F-16. The most interest for us today is the fault-tolerant 270 volt power system. So that little guy there, that F-16, which is now retired at the Wright-Patterson base, flew for 23 years and was the first plane to have a truly electric flight control system, with the majority of loads also being electric loads. That was the foundation for the Joint Strike Fighter, the F-35, which is at the bottom right-hand side. All of that plane is now a 270 volt with some smaller 28 volt subsystems, but that's really the foundation for that, getting to that all-electric prototype in the F-16 in the year 2000. Now, going back again to some of the loads and flight control technology, during the 20s, 30s, 40s, into the 50s and 60s, the hydraulic system was the standard. Obviously, if you want redundancy or reliability in your aircraft, you need redundant paths for that hydraulics, which meant 3 times as many pipes as you'd really prefer. And all of those pipes are very heavy, very difficult to install and also to maintain. So if we look at the history of Airbus, for example, the A310, which is about the same size as a Boeing 737, was a completely hydraulic system. But when Airbus were preparing the first plans for the A380, which is the behemoth plane, which can take 835 people in all economy seating, they realized that the tail fin alone on that plane is the same size as both of the wings on the A310. So hydraulics really were not up to scratch in controlling the avionics on that plane. So the A380 was one of the first commercial aircraft to have a hybrid system where Airbus call it a 2H2E, which is 2 hydraulic systems and 2 independent electrical systems. So electric power goes to the actuators, and an actuator is just simply a device which performs a specific mechanical function, like raising a wing flap or dropping the nose wheel on the undercarriage. So now this system operates on an electrical harness around the plane, and then we've got small hydraulic systems at the end of those electrical cables, which then power the actual wing flaps and nose wheel, etc. itself. Now, a note on some history. The forerunner to this kind of electrical / mechanical actuator, and also one of the forerunners of a relatively high voltage DC system, was the Avro Vulcan, which was a British designed and built bomber which first flew in 1952, and that used 4 22.5 kilovolt amp generators on board coming from the engines to create 112 volts DC. And at the time, instead of calling it an EHA, an electrical hydraulic actuator, it was called a powered flying control unit, which is very British. So the Vulcan was a few years ahead of the A380. Obviously, the A380 is a huge plane in comparison. So when we look at different sizes of airplanes and different power required, so these are the electrical powers required. So the Airbus A380, the big guy, 450 kilovolt amp variable frequency generators from the TRW company. Note that the Dreamliner is actually a smaller plane, but it has more electric power available. More of those loads in the Dreamliner are pure electric rather than being the electric/hydraulic hybrids. So again, as the Dreamliner would probably started design maybe 5 years after the A380, taking advantage of the new technology, going to an even more electric aircraft. As we get down into the unmanned aerial vehicles, or rather the higher end of those, then we look at the Predator C Avenger. That's not the original Predator. This is a larger device, more akin to a simple flight pilotless plane. And the Global Hawk, these are the big guys. Those are a 20 kilovolt amp, 25 kilovolt amp coming from the turboprops. But we are talking about a lot of power in electrical form, as well as obviously the mechanical thrust coming from the jet engines. Looking at a little more detail on those UAVs, if something is a hand-launched or a catapult-launched UAV, it's probably going to be maybe a lithium-ion battery at 10.5 volts or a small gasoline motor. In that case, it's already low power, and so having a low voltage bus like 10.5 volts or 28 volts makes a lot of sense. As you get into the larger devices which require a medium or a short runway, then obviously you get into the higher power, and here the engine is put into a variable frequency generator. We get out the wild frequency, we convert that to 270 volts DC, and then that is carried around the system. So depending on the size of the UAV also dictates in large respect the distribution bus voltage. Now, coming to the exciting topic of military standard specifications. I think the most important thing on this page is the website of assistdocs.com. This is a US government website, and any of the MIL standards are available from this site free to download in PDF form. So if anyone says, well, can I get my hands on a copy of MIL standard 1275 or 810 or 883, this is the place to go. So assistdocs.com is your favorite reference site, and I'm sure you'll all be drifting off there very shortly. Regarding 270 volts DC, in terms of the voltage spec itself, 704F is the latest incarnation as the US MIL standard. It should be noted that MIL standard F has a more tame input voltage and transient spec than previous generations. So if you go back to MIL standard 704D, then that had extreme excursions in voltage. So if you're designing for a specific system, you need to check which reference number it is that they are designing to. If it's a brand new build, it's probably 704F, but if that same device is required to retrofit maybe into a C-130 Hercules or a B-52, then chances are it's using an older electrical generation system which might require 704D. So just a note of caution that the newest spec may not cover all of the customer's requirements. The RTCA DR160 is obviously the commercial variant. They overlap in most areas, although military applications do have higher stresses now and again due to the workload. So it pays to take good care of which spec the customer is referring to and really go through these specs in detail. In terms of EMI or EMC, 461F is the latest MIL standard, which applies also to the DEF standard 59411. That's a UK reference. And in terms of the quality, reliability, we're looking at 810, 883, etc. This is the shake, bake, rattle, roll, temperature cycling for components and systems to make sure they survive. And in Vicor for our MIL cots, we obviously make sure everything adheres to the 810 or 883 where applicable, going from -55 degrees C up to 100 degrees C case for all of our MIL cots products. Now, regarding the 270 volt DC voltage, that obviously is a nominal value, and you can see from the table on the left and also the chart on the right hand side, after a certain point there is a steady state max and min, which is 250 volts up to 280 volts. So your system needs to be able to run there forever, and that is a stable voltage. However, you'll notice that, especially on the top right, there are transients down to 200 volts and up to 330 in which your device must still operate. You may be able to derate it during that time period, but it must still operate. And then on the bottom right, there are even more extremes of undervoltage and overvoltage where the device is allowed to self-protect, or you could have an upstream protection device before the converter. So if, for example, you drop down to 10 volts DC coming in, it is okay for the device to go to sleep and then wake up again once the voltage is back within the range. So different voltages depending on the transients, and transient being a certain time period for a certain voltage. And all of these I simply copied and pasted out of the 704F spec from the assistdocs.com website. Now, when it comes to the power conversion, the Vicor philosophy is called a power component methodology, by which we create very high efficiency, small size, so high power density, and very flexible building blocks. And these building blocks, like Lego, are the basis for many, many different systems or configurations to suit the various applications. So we have building blocks with an AC input or a DC input. We could have isolated, non-isolated topologies, regulated, non-regulated, etc. And obviously, if you have a building block, you can put them in parallel for higher power. There are also instances where you can stack inputs and outputs to withstand different voltages or to create different voltages on the output. So a very, very flexible system. The drawing on the right-hand side shows AC input or high voltage DC inputs with different ranges, and going to a central hub, in this case the 48 volts, and that is obviously a selve voltage. That's the safety extra low voltage, which means it's okay for people to touch. And then from that 48 volt hub, you take it down using, again, different Lego bricks to the various loads, whether they're plus or minus, or less than a volt, hundreds of amps, or a few watts. Obviously, in a military system, we'd be talking 270 volts DC coming in, and then usually a 28 volt bus, according to mil standard 1275, in that midpoint, although there are many applications like an actuator for the nose wheel. For example, a company like Moog might take in 270 and just have a very small converter within that device directly driving the actuator for the nose landing gear. And obviously we go from 270 volts directly to radar jamming transmitter amplifiers rather than going through a separate 28 volt bus. So some of those building blocks the first two are a regulator and a transformer, and seminar number 2, which was on December the 12th, went into these two topologies in depth, including the switching waveforms and more features of the different topologies. So today we've just got a single page for each, but I would encourage you to go to the archived presentation that was on December 12th, seminar number 2, that looks at these components in full detail. So with that said, at a very high level, the regulator Lego brick is a non-isolated buck boost converter. Now, key attributes to this converter are that it is fully zero voltage switching, which means you don't have trapped gate charge in the FETs as we go through different switching cycles. Therefore, we don't have heat generated in the switches. Therefore, we can run at a higher technology magnetic materials, therefore we can make the transformers and inductors smaller, therefore the PCB gets smaller, therefore parasitics are reduced as well. And this positive spiral of technology and benefit continues and continues. So one other thing to notice about this is that during the switching cycles, or rather a transition from, let's say you are boosting and then you go through that voltage sweep and start to buck, this device does not have any glitch or any hysteresis. The switching phases, the steps by which the 4 main switches are actually turned on and off, the sequence does not change, but the time period in each of those switches does change. So you get the bucking and the boosting, or in the case where the input voltage is the same as the output voltage, we can create a virtual wire that goes through the device for highest efficiency. In terms of the implementation in real life, what we have in mass production today are devices which are in our what we call a full chip package and a half chip. These are about 1-inch area and a half-inch area devices, and we're up to 500 watts and 250 watts respectively in those devices as a buck boost unit. Very high efficiency, over 97%. Our roadmap for this year is to have devices which will be up to 1 kilowatt in a slightly new packaging technology we're calling the chip platform, and we're measuring the chip in dimensions the same as a resistor, for example. We might say an 0805 or an 0603, measured in thousandths of an inch. In this case, we're focused on millimeters, so a 3623 is 36 millimeters by 23 millimeters as we saw the device out of a larger block. The second of the main building blocks for discussion today in the 270 volt DC world is an isolating transformer. This is a topology known as the sine amplitude converter. And the reason it's called a sine amplitude converter is you put in a DC signal, the control IC operates the MOSFETs, and a sine wave is created which goes across the transformer barrier, is transformed by the ratio of the transformer, the K factor. This is a fixed ratio device, and then full wave rectified on the second side, again to regain its DC nature. So this is an isolated DC to DC converter. Now, a few very, very special points here. The first one is that it is a pure sine wave as it crosses the transformer, and the amplitude part of the name comes from the fact that that amplitude varies with load current. So you see, if we go through a transient step, and again this is on seminar number 2, you'll see the amplitude of that sine wave varies with the change in load. Now, this system is also unique in that it is an LC resonant system converter, but it is a fixed frequency, which makes it very easy to do any EMI filtering and for us to do the control. Now, the resonant tank itself, the LC, the L is actually the leakage inductance of the main transformer. It is not a separate inductive element. And the C, that's a small collection of physical capacitors within the device. So this is a zero voltage and completely zero current switching isolating transformer with that fixed ratio. Other special points about the topology. Number one, it's reversible. Let's say you had a 1/4 transformer and you put in 48 volts, you'd get 12 volts on the output. If you put 12 volts on the output, you get 48 volts in the input. Maybe not a strong point for 270 volt applications, but there are many things in the transportation, earth-moving equipment world where you really want to go from 600 volts or 800 volts down to a 24 volt battery and then back again. So that's just one to take notice of. The other thing is that this device, because it doesn't actually store any energy, it means that it is thermally rather than power limited. So either for a short amount of time, or if enough coolant or cooling can be applied to the device, we can get 2 times the power rating out of this device for a short period. that enables us to do some component count area size minimization techniques later. So what we have today in the full chip is up to 330 watts. We've actually released a high voltage bus converter in the telecom space. Now the telecom world, that runs from the 260 volt DC up to 400 volts DC as part of the ETSI, or European Telecom Standards Institute specification. And we've got that nominal 380 down to 48 volts, 1.2 kilowatt converter released to production. And if you care to go on the Vicor site and look for DC-DC board mount power, you'll see that guy there. Now obviously for the 270 volt, we need to make sure we optimize for that 270 volts and then convert down to something useful as well. And we'll go into that a few more slides. So the first two elements are a non-isolated regulator and then an isolating fixed ratio converter. The third topology is a combination of those first two. So as you can see from the simple schematic on the right, we have our 4 switches from the ZVS buck-boost converter, but now that the inductor is changed into a true transformer and then rectified with a full wave rectification again. So in this way we've got DC on the input and DC on the output, but in the middle we now have a regulating transformer stage. So while this is not as efficient as the two-stage approach, it is very, very power dense, and especially for power levels up to say maybe 500 watts or a kilowatt, is a very small, neat, very light solution for many different applications. We'll come on to a few diagrams later. So overall we've got the buck boost and the transformer for very high power systems, and then what we call the double clamped zero voltage switch converter for lower power applications. And in a 4623 device, so this is 46 millimeters by 23, we have prototypes now. We hope to release next month at T grade at least, a 450 watt device which can reach 600 watts with the correct cooling, and we plan to make a full Milcott's 704D version of that. And obviously if we do it for 704D, it also covers 704F applications as well. So when it comes to the applications itself, everything in a plane is about weight and size, and obviously you have to have the right amount of power to go with it to run those loads. So swap is the standard terminology used in the industry. And the chain of events, starting on the left-hand side with the Vicor topologies and techniques like megahertz switching, ZVS, DCS, and also capacitance multiplication, which we'll go into later, they enable us to do different things within the module, and again, that module enables smaller, lighter applications. And once you've got less weight, that's really where you get your longer range, more effective missions, and with a shorter takeoff, have more flexible deployment. So it all comes down to less weight, which comes from the Vicor innovations on the electronic side, resulting in real-world benefits on the right-hand side. So how do we get from 270 volts down to something useful using these building blocks? So the first example is where we have 270 volts, mil standard 704 on the left-hand side, and we want to get to either, say, 28 volts for a gallium arsenide or 50 volts for a gallium nitride transmitter. The first thing is to take that 270 and drop it down and isolate it to something more usable, more feasible. So here what we have is our isolating transformer, that sine amplitude converter, going from 270 volts down to 45 with a K of 1 divided by 6. That's the transformer ratio. Once that's down to a reasonable level, that 45 volts, remember it still will vary with the input transformed by the ratio. So that's still a varying 45 volts depending on what the 270 volts is doing upstream. And so now we take our buck boost non-isolated engine and we define a stiff DC voltage, and we trim it up and down using that buck boost to match the right voltage required for the transmitter. And in this kind of application, there's usually a large capacitor bank at that transmitter voltage from which the transmitter will draw during pulsed power events. And obviously, having that Lego brick approach means that we can optimize the whole system by simply adding more blocks as we need them for higher powers. Now, if we compare this in terms of the size, weight, and power to traditional brick-based devices, the result is quite amazing. Due to the higher efficiency, the smaller size, we can first of all simply look at the number of components and the size and weight of those components. But then we start to look at the extra, very tangible benefits of this new system. If you have a higher efficiency, you have less loss. Therefore, you don't need as much heat sink or cooling as previous. That means it's smaller and lighter. If we're running at a higher frequency, and especially a fixed frequency, it means the EMI filter is also much smaller, much lighter. So there are compounding benefits by going to a fixed frequency, higher efficiency unit. So here with this 270 to 50 volt example for the gallium nitride, the 2.4 kilowatt block becomes about 5 times smaller using the VI chips in mass production today, and then looking ahead to our chip platform, we get another 2x on that, so a 10 times smaller and lighter solution than traditional brick approach. Now then, one other thing about the separation of a regulator and a transformer, or as we say in Vicor, it's the factorizing of the architecture. So you have an element which is the regulator and a separate element which is the transformer, is that you can use the strengths, the attributes of these components individually or combined where you need to. So the drawing at the bottom is, let's say that's a 48 volt input with a 48 volt input with a 1.5 volt load. And to have an isolated and regulated system, you need a regulator, which is our PRM pre-regulator module, and then a transformer, which is our VTM, that's our voltage transformer module in this case. So this creates a regulated, isolated, stepped down solution. However, one of the attributes of that transformer is that it is very, very low impedance. So taking into example the 1 divided by 40, that's 1 divided by 40 transformer ratio that we have for some of our low voltage devices, the impedance on that is less than 1 milliohm from DC up to 1 megahertz. Now that means that usually the load would be pulling power from a capacitor bank at that 1.5 volt point to maintain the voltage stability. Instead, the load, when it goes from sleep to full power, for example, it can see through the transformer and up to the higher voltage level. And as the energy stored in a capacitor is proportional to the square of the voltage, that 48 divided by 1.5, everything squared, means that you have a 1,000 times reduction in the capacitance required. Now, obviously, we're going from a kind of capacitor, maybe an OSCON or electrolytic at the 1.5 volts. We can also change the technology to make a small surface mount ceramic chip capacitor at that 48 volt rail. So we're really improving the density, the weight of the whole system, and in some cases getting rid of electrolytics, which in military applications can be a reliability risk. So this is what we're calling the capacitance elimination technique, which really comes into its own when we look at downstream pulsed power applications. In those kind of systems, and here we're again starting with 704, or the 270 volt rail on the left hand side, and now we're going to a low voltage transmitter chip. So this is a 2.5 volt silicon germanium device. On the left hand side, we've got the standard transformer regulator going to a fixed voltage. And you'll notice that the bulk capacitance for the stability and the extra pulse power of that transmitter, we've moved it up to that 40-volt point, which obviously has a resulting huge saving, 250x times less capacitance. And again, with the Lego brick nature of these modular applications, we can size the upstream system to trickle charge or average charge that cap back. So we use only the amount of devices we need to do that function. And on the right-hand side, if you remember that the sine amplitude converter had a 2x overpower rating for short durations. So now, if we have a pulsed transmission from that silicon germanium amplifier, then we can use that short duration overpower spec in the bus converter and reduce the number of bus converters used. So obviously, we get the same power peak on the output. We use less components, which again is less size and less weight. And we can optimize the architecture and scale of the system by optimizing the left-hand side for trickle charge or average charge, and then the right-hand side after the cap for the pulsed power duration. So this is, again, another example of using those very flexible, very efficient building blocks to create different systems. And if we do this kind of system with that low voltage output, we're really at the 8 times, getting on for 10 times smaller and lighter than a traditional system. Again, the additional savings we haven't added into that calculation for less heatsink, less EMI filter, and also because we're going 256 times less capacitance, the physical size and weight and potentially also improved reliability of those caps really comes into their own. Now, when it comes down to smaller loads, and by smaller, again, it's that kind of 500, 750 watt, 1000 watt area running from the 270 volt DC bus. Here we're using our DCM, that's our DC to DC regulated unit, using the double clamp zero voltage switched engine, the topology. And so here we've got the wide range 270 volt mil standard 704D. We've got quite a wide input voltage spec on this device, and we can create a very nice 28 volts bus for downstream systems. And obviously 28 volts is the mil standard 1275 reference point. From there we can go through various combinations of components, again plus or minus voltages, very low voltages with high current, or just give me 15 volts and 3 amps, thank you very much. So this is again the component methodology approach to get a very neat system in a very small size, still very high efficiency and very flexible. We can also look at some more of the traditional Vicor units. Vicor back in 1981 invented the brick for the industry, and here are some of our existing and still very much alive and maintained and growing portfolio of brick products. In this case, again, we go 270 volts down to the 28 using our maxi size, which is the full brick converter. But you'll also notice that we have what we're labeling here as an MFM EMI filter. That is the Milcott's filter input attenuation module, which is a long way of saying it does EMI and the transient voltage suppression covering mil standard 461 and mil standard 704. So this is a very, very useful, again, Lego building block. Just drop this guy in and it will look after all of your filtering functions on the front end of that power chain. So again, depending on the mounting style, depending on the application, we have the different packaging options, different topologies to suit all of those airborne apps. The power component methodology is ideal for our customers to use in their own design centers, obviously, to create different applications. We offer full factory-based and field-based support for that. In addition, there may be times where your design team is overloaded, or you might not have experience in a certain area, and there also Vicor can help with our custom power team. So we have teams spread around the US and Europe, which will use Vicor devices and other components as needed to make complete turnkey solutions. So you can go from a piece of paper, a specification, to a fully designed, tested, certified product for your systems. So Vicor is a very broad portfolio, and we can offer that portfolio either as those modular building blocks or as complete turnkey solutions. And a lot of those turnkey solutions and the modules have been combat proven or flight proven in the case of the MIL Standard 704 in the field. So here are a few of the applications or the vehicles, whether it's a land-based vehicle or a water-based or an aircraft using the different Vicor units, and all the way down to the NASA Space Shuttle and the International Space Station using Vicor components. So we do have a very strong track record of rugged, high-performance components for the military and commercial airline units. Just looking at this list, I think we missed one off. The Boeing 787 Dreamliner. I know at least we're in the wing de-icing section on that. So that's another one we need to add to this list. So that was the end of the 270-volt specific seminar. As Alex introduced, we are running through a series of these seminars. And so this is number 6 in the sequence, the 270-volt commercial and defense aircraft. The first two were an introduction and also that deep dive on the components. So if you'd like to look at those, then please look at vicorpower.com and look at the rebroadcasts. The next three, based on the data centers, the infrastructure and commercial buildings, had special guest presenters from HP, from Emerson and Universal, and also the Fraunhofer Institute in Germany for the commercial buildings. We're very excited to have a gentleman by the name of George Hamilton, who is the Assistant Deputy at the U.S. Army's Research and Development Engineering Command in Warren, Michigan, who has agreed to do our seminar on land-based 600-volt specs. So the reason why that one is now TBD is that we're just going through a few hoops to make sure that he can give the full presentation. But we're very excited to have him on board, and hopefully within a few days, everyone that registered for this seminar will receive an email of the right date for Mr. Hamilton to present the land-based vehicles. Very exciting topic. The picture there is the Paladin self-propelled howitzer. It's also been Stryker vehicles, Joint Light tactical vehicles, and an ultralight vehicle, all powered with a 600-volt DC grid. So very, very interesting one there. As a result of that, we will be combining the 800-volt spec from earth-moving equipment with the 400 volts for automotive, whether that's cars, trains, or trucks. So that will probably be a longer running seminar on March the 6th. And fingers crossed, we might also be able to add one on high voltage DC in ships towards the end of the seminar series as well.